Welcome to This Explainer. Today, we're unpacking something totally wild, the unexpected reality of teaching foundational artificial intelligence skills to 8-year-olds. And here's the kicker. They are doing it without ever needing to touch a keyboard or look at a screen. It's a completely fresh approach to education, and honestly, it might just make you rethink how you solve your own daily problems.
Sounds like a high-tech task reserved for hackers and computer scientists, right? But what if I told you that third graders are actually learning to use ancient cryptography right now? They're using things like the Caesar cipher, which Julius Caesar literally used back in the 1st century BCE to encode and decode secret messages. They are learning the core mechanics of encryption, like shifting alphabet letters by specific positions, way before they write a single line of actual computer code.
So here's our game plan for today. We'll look at future skills for kids, what computational thinking actually is, how to spot hidden patterns, breaking down problems, thinking like an algorithm, and finally, a real-world application.
All right, let's dive into part 1, Future Skills for Kids. We're looking at the vision behind the National Education Policy 2020. The goal here? It's definitely not just about memorizing facts for a test or learning rote computer skills. We're talking about a massive shift away from standard memorization and stepping into true competency-based experiential learning. The whole vision is to empower students with cognitive agility. We want to give them the intellectual backbone they absolutely need to thrive as creative problem solvers in an AI-driven world.
Moving on to part 2. What exactly is computational thinking? Let's break down the cognitive foundation.
Here's the big takeaway. Computational thinking? It's not actually a software requirement at all. It's a fundamental human cognitive process. It's all about simulating the thinking processes associated with human intelligence so that a young student can approach a messy, real-world challenge systematically.
When you take these kind of intimidating academic terms and translate them into everyday language, it really clicks. Teaching kids AI is really about teaching them playful visual problem solving. It's about looking at total chaos, finding the pattern, breaking it into little pieces, and creating a step-by-step recipe to fix it.
Let's put this into practice with part 3, spotting the hidden patterns, or as I like to call it, filtering the noise.
Okay, look at this. Your brain is instantly hit with a flood of chaotic shapes and numbers, right? We've got triangles, squares, pentagons, circles, and digits from 1 to 9 everywhere. But the question simply asks, which number in the options can be formed using the digits in the circles only? Can your brain quickly tune out all those visual distractions and isolate just the data you need? See, by completely ignoring the noise, a student zeroes right in on those circles and finds the digits 6, 1, and 4. And boom, those digits can be arranged to form the number 146. It seems super simple, but it is literally training the brain to pull essential data out of a chaotic environment. And that is a foundational skill for data analysis.
Next up, part 4, breaking down the problem. Let's see how we decompose moving variables.
This is a fantastic visual logic test. Specifically, we're looking at how to decompose page 15, puzzle number 3, into manageable parts and find its solution. We have 3 rods placed at different starting levels on a grid. Rod A is at levels 2 to 4. Rod B is at 3 to 5. Rod C is at 1 to 3. Now here are the instructions. Rod A moves up 1 level, Rod B moves down 2 levels, and Rod C moves up 2 levels. After all that, how many levels do they all share? If you try to visualize all 3 of those rods moving in your head at the exact same time, yeah, your brain is probably going to short circuit. It's just too much overlapping data.
But if we decompose this exact puzzle into bite-sized pieces, the impossible becomes totally obvious. Step 1. We track Rod A independently. It moves up 1 level, so 2 to 4 becomes 3 to 5. Step 2. Track Rod B independently. It moves down 2 levels, shifting from 3 to 5 down to 1 to 3. Step 3. Track Rod C independently. It moves up 2 levels, going from 1 to 3 to 3 to 5. Now, for the final step, we just compare those decomposed end states, 3, 5, 1, 3, and 3, 5. Suddenly, it jumps right out at you. Level 3 is the only common ground between all 3 rods. That, my friends, is the absolute magic of decomposition.
All right, part 5, thinking like an algorithm. Let's create some logical pathways.
In this one, the kid is basically acting as the programmer. They've got a grid with spots like home, school, cafe, office, and gym, along with 4 different visual pathway blocks. The mission? Get from point A to point B using only these logic blocks. You have to select the exact pieces needed to map a continuous path starting at home and ending right at the school.
This is such a brilliant way to demonstrate building a sequential algorithm without writing a single line of actual code. You can't just slap blocks down randomly, you gotta think 3 steps ahead. First, you have to grab the block that drops down from home and turns right. Then, you find the block that continues the path horizontally. And finally, you pop in the block that curves upward exactly into the school. It's a physical representation of coding logic. Literally, if this block, then that direction.
Let's wrap things up with part 6, the real-world application. It's time for the jumping man puzzle.
Okay, here's a slightly trickier multi-step math logic problem. A man jumps forward 3 feet, but gets dragged back 1 foot. In every subsequent jump, both of those distances increase by 1 foot. So how many jumps does it take to reach a pole that is 12 feet away? This is tough because the variables are changing with literally every single movement. The forward jump gets bigger, sure, but so does the backward drag. If you try guessing, you'll probably get it wrong, because our brains inherently struggle to calculate escalating dual variables simultaneously.
But if we algorithmically map these data points out in a table, the unseen pattern just pops right out. Jump 1, forward 3, back 1, he's at 2 feet. Jump 2, forward 4, back 2, he's at 4 feet. Jump 3, forward 5, back 3, he's at 6 feet. Now pay close attention to the 4th jump. He starts at 6 feet, and his next forward jump is exactly 6 feet. 6 plus 6 is 12. He actually touches the 12-foot pole before the backward drag even has a chance to happen. By mapping it out sequentially like an algorithm, an 8-year-old spots the trick that completely fools most adults.
Seeing these cognitive skills in action really makes you stop and wonder, doesn't it? We get so obsessed with learning the newest software or the latest coding language, but looking at how these 3rd graders are deconstructing the world, you gotta ask yourself, is your foundational problem solving as sharp as an 8-year-old's? It's definitely something to think about. Keep decomposing those problems, and I'll catch you on the next explainer.